Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras in India, and my email addresses are given here for you to write to me on this or any other subject related matter. This lecture will provide an elementary introduction to variational principle in quantum chemistry. And of course, I would try and make it as non-mathematical. I wouldn't do any formal introduction to variational principle as a whole, but will restrict to the most basic elements that we recognize in quantum chemistry. A very good elementary account is given in two books that I have mentioned here, and both of which have influenced my own learning and applications of quantum mechanics to chemistry. One is the book by Donald McQuarrie, Quantum Chemistry. I'm sure I mentioned this earlier. And the other is the book by Levine, I.N. Levine, also on quantum chemistry. They are both quite old, but they have very good learning materials. Now, variational principle was introduced in quantum mechanics for energy. It's called the energy minimization principle. First by Professor Erwin Schrödinger, whose equation we have been trying to understand for model systems, namely the time independent equation H psi is equal to E psi that you have been working through this course. This is one of the most significant contributions by Professor Schrödinger himself on the energy minimization principle. In a nutshell, what it says is that for any arbitrary state psi of the system, that is wave function psi, if we choose, or if the system is in any arbitrary state psi, and it is not one of the eigenstates that we are trying to get by solving the equation H psi n is equal to E n psi n. We do not know this yet. For any arbitrary state psi, the average value energy calculated, the lowest, for that state is psi star H psi d tau, and if the wave function is not normalized, you also divide it by psi star psi d tau. The average value calculated is always higher than the exact ground state. E is always higher than or greater than or equal to the exact ground state of the system, which we will denote by E1, as long as the wave function is arbitrary, and E will become exactly E1 provided the wave function psi becomes the eigenfunction psi 1, corresponding to the equation H psi 1 is equal to E1 psi 1. That is, no matter whatever you do, whatever approximation you provide, the average value for the energy through the calculation using the Hamiltonian that you obtain will always be greater than the lowest exact eigenvalue for that system, and therefore, this lowest eigenvalue, or what is called the ground state eigenvalue, provides what is called the upper bound to all our calculations. We know that we are on the higher side of the error, not on the lower side of the error. This is a principle, and I will immediately demonstrate this with a simple statement of the eigenfunctions and expressing wave function as a linear combination of eigenfunctions. You will see that in a few minutes. This is an extremely important principle because what it says is that if you want to get the exact ground state eigenvalue, you have to search for the exact eigenfunction, the ground state eigenfunction. Therefore, if you obtain or you provide eigenfunction using some parameter and the energy is calculated as a function of that parameter, then you want to get the minimum for that energy. There is a mathematical method provided by the variational principle, namely minimizing that energy as a function of the parameter. We will see these things right away. If the energy is obtained through a function and a parameter C, one parameter here, but it can be many. This is the average value E, and therefore the average value E is a function of the parameter C. Then if you minimize the average value with respect to that parameter and then calculate the average value, you would see that that's the best you can get. And your idea of choosing the parameter is that the wave function that you choose, psi, which is also a function of that parameter, the wave function that you choose should be chosen in such a way that it is closest to the possible exact eigenfunction. I mean, depending on the system that you have. If the system is close to harmonic oscillator types, then you can use the linear combination of the Gaussian functions. If the system is that of a Coulombic system, like in the case of chemical, in the case of molecules, obviously Coulombic interactions are important. Therefore, the starting point could be something like the hydrogen atom wave functions for each and every electron, or a slightly better approximation and so on. But the point is, no matter what you choose, the average value for the energy that you calculate is going to be higher than the exact ground state. Let us look at this by a simple illustration. Let's assume that H of psi n is equal to En of psi n, or a system with some atoms and molecules, whatever it is, okay? And let us assume that n is finite. It will never be, but, and the state of the system, let it be an arbitrary state, and in the same line as what we did in the last lecture, this will be k is equal to 1 to n, some constants C k psi k. Let us calculate the average value for the energy using Ck psi k wave functions. These are the eigenfunctions 1 to n, and C is the linear combination coefficient. And remember that the psi k's are given by the, or I mean, they have this orthogonality properties. Psi k star psi l b tau is delta k l. Therefore, if you calculate the average value, this would be the integral psi star h psi d tau, and let us assume that the wave function itself is normalized, psi itself is normalized, namely psi star psi d tau is 1, which means that if we use the expansion of all the eigenfunction, this means that k is equal to 1 to n sum over Ck square is 1. Okay? Let's keep this in mind. Therefore, the expectation value for the energy is given simply by this. And if you write this up explicitly, it is sum over k, psi star is Ck star, psi star k, psi, h acting on some L, the same summation, but we will use a different index, C L psi L b tau. This is psi, this is psi star. We expand this. This is sum over k, sum over L, C k star C L, integral psi k star h psi L d tau. And since the k, psi k and psi L are all eigenfunctions of the Hamiltonian, this will give you E L psi L. Therefore, the integral is psi k star E L psi L d tau, just this part alone, and that is equal to delta k L E L. So, if we substitute that here, then the average value for the energy is sum over k, sum over L, C k star C L delta k L E L. Because of the delta k L, if you expand the sum, k is equal to 1 to n, L equal to 1 to n, k and L have to be the same. Therefore, there is only one sum, which is sum over k or L, whichever is the index you can choose. It is C k star C k E k, because we have removed the sum over L with this orthogonality. Now, this is the average value for the energy. Okay. So, let us write this, expand this. It is E1 times C1 square plus E2 times C2 square plus E3 times C3 square plus and so on. Okay. Let me introduce to this sum, add and subtract. Let me add and subtract E1 times the sum over k equal to 1 to n C k square. We are adding that, and therefore, we also have to subtract the same thing. E1 sum over k is equal to 1 to n C k square plus all of this, E1 times C1 square plus E2 times C2 square plus. Now, you can rewrite this whole summation as follows. Okay. This term is going to give you this particular term. This is going to give you E1, okay, because the sum over k square is 1. But now, let us take this into this form. Therefore, this is E1 C1 square. There is also an E1 C1 square that gets cancelled out. Okay. But then the rest of it will be E2 minus E1 times C2 square plus E3 minus E1 C3 square plus etc. plus En minus E1 Cn square. The eigenvalues are chosen in the order that E1 is the lowest energy, E2 is the next higher energy, E3 is the next higher, and so on. Therefore, the energies H psi n, the energy is given by this equation, H psi n is equal to E n psi n. Let us assume that the increasing order of energy is E1, E2, E3, etc. Then you can see that all these coefficients are positive, all are positive, and this is definitely positive because of our choice of the E1, and you can see that the average value for E is greater than E1 because it has the additional terms. When will the average value E become equal to E1? Obviously, not when E2 is equal to E1, because these are different eigenvalues. They are never going to be equal. What is important is these will be, this energy average value will be equal to E1 if C2 square is 0, C3 square is 0, etc., Cn square is 0, which means the psi that you have is now simply C1 psi 1, and since psi is normalized, C1 is, the phase factor is 1, we can remove that, the normalization coefficient. Therefore, psi has to be psi 1 if the average value E is equal to E1. For all other choices of psi, and for all others, no matter what coefficients you choose, psi n, the average value E will be greater than E1. So, this is a very simple illustration that unless you happen to choose the trial wave function psi, which you think represents the state of the system, and you want to find out all the coefficients C1, C2, Cn, etc. by solving the equation. Okay. Unless you choose the trial function by coincidence to be exactly the same as the ground state eigenfunction, the energy eigenvalue that you calculate will always be greater than the lowest exact eigenvalue system. That is what this whole proof is about. So, it is a very simple way of understanding that is our scale, that is the bottom that we want to calculate, and very often in quantum chemistry, the calculation of the lowest or the ground state eigenvalue of a stable system is called the search for the, or it's a holy grail. This is fundamentally important for all quantum chemists, that they should try and get the exact lowest eigenstate possible, and that will give you obviously the molecular geometry, and all the equilibrium properties can be calculated using the lowest eigenvalue and the lowest eigenfunction. Therefore, it is very important that variational theorem tells you you can never do it unless you happen to accidentally get your eigenfunction to be the same as the lowest eigenfunction. But variational theorem tells you, you do not have to worry, no matter what you calculate, all the calculations that you have done are greater than the lowest. Therefore, it is the upper bound that it is providing, and we have to fine-tune our wave function, parameterize our wave functions in such a way that we minimize whatever energy that we get as a function of that parameter, and try to get the best possible wave function that is closest to the eigenfunction of the system. This is what the variational principle is. You will see some examples, and therefore, it might be easier after seeing the examples to go back and look at the theorem again. Let us take a simple example. H is the harmonic oscillator. It is minus h bar square by 2m d square by dx square plus half kx square. Now, we will tweak this example. We know the exact solution for the harmonic oscillator. Therefore, how do we understand the variational principle? Let us choose an arbitrary wave function and calculate the energy and minimize the energy as a function of the parameter of the arbitrary wave function. What is meant by the parameter here? Psi is equal to, let us assume that it is C e to the minus lambda k lambda x square. Lambda is unknown. And we want to find out wave function psi as a function of lambda as well as x, of course. Okay. Lambda and x. X is the coordinate for the whole wave function, but lambda is the parameter with which we evaluate different wave functions with different values of lambda to see what is the best value of lambda that would give you the exact eigenvalue or will give you closest to the exact eigenvalue. But you know that we have already guessed the wave function very close to that of the harmonic oscillator wave function. You know that the ground state wave function of the harmonic oscillator is alpha by pi 1 by 4 e to the minus alpha x square by 2, where alpha is obviously k m by h bar square root. You know that already. This is the exact solution we know. Therefore, if you do this average energy calculation using the psi, and if you get the average energy as a function of lambda, and if you minimize the average energy as a function of lambda is equal to 0, you will get obviously lambda is equal to minus alpha by 2, sorry, plus alpha by 2, lambda, there's already a minus sign here. You will get that as the answer. But the illustration is to tell you the process by which variational principle is used in quantum mechanics. Okay? Let's do that. Psi of x is equal to c e to the minus lambda x square. The average value E is going to give you the c star, c square, e to the minus lambda x square between minus infinity to plus infinity. That's a harmonic oscillator coordinate. And then you have a minus h bar square by 2m d square by dx square plus half k x square e to the minus lambda x square dx divided by c square e to the minus 2 lambda x square dx from minus infinity to plus infinity. This is, let's first do this because this is normalization integral. You know, this has to be equal to 1. So if you want to do that, that will give you the value for c. This is c square times z to the minus 2. Remember, root pi over a, so it is root pi over 2 lambda. And that would be, that means c is 2 lambda over pi 1 by 4. Okay. This is the normalization constant. Therefore, the average value E is 2 lambda by pi to 1 by 2, which is c square. And then you have the integral e to the minus lambda x square times the derivative acting on e to the minus lambda x square dx. So you can do this. D square by dx square on e to the minus lambda x square will be d by dx on minus 2 lambda e to the minus lambda x square, 2 lambda x e to the minus lambda x square, and that gives you minus 2 lambda plus 4 lambda square x square e to the minus lambda x square. So that's a derivative. Then you have, if you multiply this by the minus h bar square by 2m d square by dx square on the same, you get minus h bar square by 2m minus 2 lambda plus 4 lambda square x square times e to the minus lambda x square. Then you have a half kx square on e to the minus lambda x square. So, the integral that you have to now solve is 2 lambda by pi to 1 by 2 minus h bar square by 2m 4 lambda square x square minus 2 lambda times e to the minus lambda x square plus k by 2 x square e to the minus 2 lambda by x square. All of this differentiated. The answer will turn out to be h bar square by 2m times lambda plus k by 8 lambda. This will be the average value E as a function of lambda. Therefore, if you take the derivative of this with respect to lambda, you get h bar square by 2m minus k by 8 lambda square. And you minimize this by taking this to be 0. It gives you lambda is equal to pi by h into root km. H bar square is h square by 4 pi square. So, use that. If lambda is given by this, therefore, the wave function is e to the minus lambda x square with the normalization constant 2 lambda by pi to 1 by 4. You can immediately see that this is one by 4 square root of 1 by 2 square root 4 pi square 4 pi square by h square into km, and that is nothing but 1 by 2 square root km by h bar square. Km by h bar square is alpha. Therefore, you can see that lambda is equal to 1 by 2 alpha. Lambda is equal to 1 by 2 alpha. And 2 lambda by pi to 1 by 4 obviously becomes alpha by pi 1 by 4. Therefore, the exact wave function E psi lambda for the average value E to become E1 is E to the minus alpha by 2 x square times the normalization constant alpha by pi 1 by 4. How do you know that this is the exact value? Use this value of lambda in the expression for the energy. The expression for the energy is h bar square by 2m times lambda plus k by 8 lambda. You just showed that lambda is equal to pi by h into square root km. Lambda is equal to pi by h into square root km. Okay. You can show that this gives you immediately the energy E is equal to half h bar omega, where omega is square root of k by m. You can verify that immediately. Therefore, you see that the energy eigenvalue that you get when you minimize the energy as a function of lambda gives you the energy E is equal to half h bar omega and gives you the parametric value lambda is equal to pi by h square root of km, and therefore, it recovers that the energy minimization as a function of this gives you the exact eigenfunction and the exact eigenvalue. That is because you started with a function which looks very close to the exact eigenvalue, namely e to the minus lambda x square. If you repeat this exercise without knowing that this is likely to be the sort of eigenfunction, but if you repeat this exercise with e to the minus lambda x, which is a problem that I will discuss in the video tutorial, you will get a different value for E, and that will be greater than the E1 in this case, which is half h bar omega. That E will be greater than this. Therefore, you see, if you choose a different function, if you choose, for example, psi of x is equal to a x square plus b x raised to 4, and now psi of x is expressed in terms of two variables, two constants a and b, and if you calculate the energy using this form, then you will get E also as a function of a and b. But you have a problem with this. This function is not the correct function. Why? Because the integral minus infinity to plus infinity of this psi of x, psi square of x, will give you infinity. What about this function? This will also give you a problem because this cannot be normalized if you want to integrate from minus infinity to plus infinity. Therefore, you cannot choose random functions. The idea of choosing these random functions wrong and then showing you that this is incorrect. The correct function that you have to choose is 1. You have to choose a function that is normalizable. 2. You have to choose a function as a function of some parameters, minimal set of parameters, and then minimize the average value of the energy as a function of all the parameters, and then put the values of the parameters into the energy expression and get the energy eigenvalue. If with all of that you won't get the exact eigenvalue unless the eigenfunction happens to coincide with the exact eigenfunction. Therefore, variational principle always tells you that you go close to the minimal value of the energy, but never exactly until you hit the jackpot. You got the function by some arbitrary choice, you got the exact eigenfunction. But it always tells you that your error is always positive. Minimize the error. Quantum chemistry is fundamentally based on the Hartree-Fock method, the advances of Hartree-Fock, and later the DFT. Every method that you see in computational chemistry depends on this fundamental principle in the calculation of the ground state energy. Okay. One last thing, what about other energies? The first exciter state, second exciter state, variational principle doesn't say anything about that. This is only true for the lowest energy E0. Nothing can be said about the first excited state or second excited state. We have to actually calculate those things using the best variationally minimized eigenfunction and linear combinations of such eigenfunctions to calculate the excited state, and hope that we are very close to the exact energy. Therefore, the verification for all these things is the experimental spectroscopy, which provides you differences between energies or frequencies as measurements. Therefore, computational chemistry must work very, very closely with experimental measurements to see what is best possible wave function and what is the best possible eigenvalue and so on. So, there is a lot more to learn, but let me stop here. This is only a cursory introduction. In the next part of this lecture, we will see 1 or 2 more examples which are non-trivial, and then let me move on to the introduction of the chemical bonding as the series of lectures to follow. Okay. Until then, thank you very much.